guys. Ready? So any questions about anything? All good? All good. So we're going to continue today with this kernel vulnerabilities topic, and I'll discuss a little bit more about what potential bugs exist in the kernel, and then we'll talk about further defense mechanisms, ability of exploitation of those bugs. Okay, so last time I think we fully covered the category which was safety violations, essentially low-level bugs related to temporal, type, and spatial safety, right? And so one might think, okay, what else can be there? Else there in a kernel? But there is like two more categories. One is protocol violations. It's essentially a protocol violation as a violation of a expected protocol between the kernel and the driver, in my example, because I'm in this paper, we're looking at a data set which includes only driver vulnerabilities in the Linux kernel. And so, for example, driver might assume that before any of the functions of its interface are called, a probe function is invoked by the kernel, right? And then that's a protocol, right? And there are multiple, lots of those implicitly written protocols of how stuff should work, right? And for example, a protocol vulnerability can be as simple as, skipping a step of this protocol. So for example, either skipping invocation of a function or invoking some function twice, or more involved vulnerabilities will revolve around something like breaking the reference counting discipline, because the kernel, there are typically two ways to pass or to control the lifetime of the buffers in the kernel. So for example, something like an SKB, and then something what represents a network buffer will have a counter, like a ref count. In any other ref counting language. And when it goes into the driver, when it's supposed to release the packet back, because it stays in the driver for some amount of time while it's sent to the device itself, the expectation that the driver will call a function which is called SKB release. So for example, if the driver forgets to invoke this function, then obviously the packet stays in memory forever. So it's a memory leak, which will potentially lead to a resource exhaustion. If the driver invokes SKB release early or twice, then the kernel most likely will do a use after free vulnerability, right? So despite the fact that it will manifest as use after free, in fact, it's a protocol violation. It's really the driver breaks the protocol, right? I mean, we will take a look later, but failing to correctly implement synchronization is a very wide class of vulnerabilities. So maybe second after the buffer overflows, we'll take a look later. Sometimes it's possible to violate the rules of preemption and interrupt disabling. So just forget to disable interrupts, and then the kernel arrives to a state in which it cannot, from which it cannot progress. Even things like failing to yield in a non-preemptive kernel is a possibility. So okay, so this is one example of a missing protocol step, which if you take a look at the diff on the board, what it does, and this vulnerability existed in multiple drivers. It forgets to invoke this function. The idea is the following. So the driver can register something what is called the word handler with the kernel. So just to explain, it's very easy. It's the drivers of the allocated an object and registered it with the kernel. And the kernel is supposed to invoke this object once in a while. Maybe it's a periodic timer, maybe it's something. The expectation, of course, is that before deleting this object, it has to be unregistered with the kernel, right? And this is exactly what the driver fails to essentially move the function, which says, okay, please unregister this piece of work. This object gets deallocated, driver gets unloaded, but the kernel still tries to dereference, resulting in the use of a free vulnerability. Right, so it's specific vulnerability from 2023, but there was a bunch of those, right? So it's pretty common because just the developer of the driver didn't realize that it has to happen. As I was saying, reference counting is a common theme for like introducing protocol violations. So here is a reference counting bug. So here, like this reference count was reduced here erroneously on a error handling pass, which was resulting in the use of a free vulnerability. So again, like just by what I'm trying to convey here is that sometimes those vulnerabilities are totally kind of, I mean, in a way they are trivial, but you can easily see that it's easy to make an error like this yourself. If you program the kernel, imagine you have several hundreds lines or maybe 1,000 lines of code, several thousand lines of code, so you suddenly didn't realize that you want to. The reason I'm emphasizing this is because just to convey the idea that despite the fact that people are finding those bugs in the kernel, most likely we will see more and more of that. In fact, I kind of claim that it will be, I don't think it's possible to really like patch all these bugs because we don't have a systematic approach to do it, right? So here's another example, race condition. So again, race conditions account for 15% of CVEs in device drivers. So it's pretty high number, as I was saying. Second to the buffer overflows. And again, they like, can you exploit a race? It's never super clear. So sometimes you can immediately achieve certain effect on the kernel, sometimes not. In this specific example, the developer makes a mistake, which can be probably classified as a logical bug, since they just use one log instead of another. It's also a spin log, it tight chaps, right, in C. But unfortunately, you know, it doesn't protect this object from the race. It's hard to like immediately guess the impact of this race, and maybe it's pretty benign. Maybe it just will result in some kind of denial of service, but we don't know. Like it requires further analysis. And again, like we've seen much more involved races in the kernel. I on purpose was picking the examples which are relatively simple, so it's easy to present in class, but there is a ton of them. An interesting flavor of a bug which exists only in the kernel. So for example, there are certain execution contexts in which the thread cannot sleep, meaning it cannot go to sleep and trigger a context switch. Just because it's so critical to finish that kernel, if the thread goes to sleep at this point, the kernel arrives to some like inconsistent state from which it cannot progress. Typically, it's some kind of a crash or infinite loop or something like that, right? And one specific flavor of this bug is that memory allocator is by default actually, if it cannot immediately find a memory allocation, it may put the thread to sleep. It takes a special flag, the atomic. So this DFP atomic says, okay, no matter what happens, do not sleep, because in this context, you cannot sleep. And so often people just forget to pass this flag. And why is it non-trivial? Because in the kernel, again, like there are like interrupt contexts, like essentially you really execute an interrupt handler. In this context, not sleeping, because the context switch interrupts are disabled, you will never get, for example, another timer interrupt to switch back, right? Sometimes it's hard to reason in which context the function is executed, because it might be executed from a different context or something along those lines. As I was saying, yet another unusual flavor of a bug in the kernel is failure to yield. So Linux kernels in specific configuration requires cooperative multi-threading, meaning that like the timer interrupts do not switch the threads. They might be delivered, might do something, but the thread will continue running, right? And so in order to make sure that there are no infinite loops, so the kernel, like the specific functions which are conceptually similar to yield, when you say, look, I know that I'm running for quite a bit of time, so it's time to probably let some other thread run. So you will invoke this yield function explicitly. And or one of those similar functions like conditional rescale, rescale function, right? And so essentially, if you don't do this, then it results in an infinite loop, like in this CDE. What is an infinite loop? Well, it's a denial of service, right? So the kernel stops responding, right? Okay. And again, I'm pretty sure that our analysis of those protocol vulnerabilities is not complete, right? So again, what we did is that we looked through all the vulnerabilities roughly. I think we had something like 240 in this data set. I'll show you in a second. And we looked through each of them trying to classify. And whatever we saw in the last 4 years, we said, okay, there is a class for this, right? And typically a class contains multiple vulnerabilities, not like a single one. If you probably extend this analysis beyond this last 4 years, you will discover more classes. So it's probably, you can see even more. And that's why, again, classification looks a little, like you might say, a little naive or incomplete, but it kind of reflects what is happening in the kernel. Okay, the next class of vulnerable attacks or flaws in the kernel, and same kind of stands for user programs as well. We call this class a logical class. So it's really just semantic violations of the program intent. So essentially, you might expect the program to return a sorted linked list or something along those lines, or a balanced tree. For whatever reason, it doesn't. There might be a bug under a specific condition, right? And the kernel is full of those like implicit invariants. Any program is full of those, right? You might say that, okay, a pointer is never null after the object was allocated and initialized, right? Just because that's typically what happens. We initialize it to a non-null value, right? However, like there are way more complicated invariants. Like we see a lot in C, where a buffer and a length of a buffer are two different fields. And the implicit assumption is that the value in that length field is actually equal to the length of the buffer, which may be broken because you suddenly like forgot to update the len or did not allocate the buffer of sufficient size, stuff like that, right? But there are like higher order invariants, as I was saying, about membership in lists, sorting of lists, or like balancing of data structures, whatever. Like you will see it, but it's a little surprising. But you will, if you look at those things, you will. I mean, yes, you will find more and more. But at some point, you will not be surprised that there are many. So one specific subset of those logical bugs is related to the fact that some device drivers are expected to enforce specific security checks. So in this specific check, the device driver says, okay, I will allow a process to execute this method of the driver, but only if the application has this admin capability. Right? So it's kind of like not every program can do it, right? And this check was dismissed. It wasn't regarding in the code of this program, the code of this SCSI driver. Essentially, people forgot to implement it, and it results in this like a logical flow. You can arguably classify it as a protocol violation, but okay, we put it into a logical category. Another one, very simple. So again, as I said, okay, question.
Yeah, so probably I come a little bit later. So these kind of bugs, they find this one by one, right? There's no ways to.
There are ways. So again, so remember when I was showing this, let me quickly show it again. This distribution of vulnerabilities by year. Some years have more bugs than others, and especially like this year. Typically, it correlates to the fact that like, a specific academic team implements a specific static analysis to look for a specific sort of bugs. So, for example, like remember we were talking about error pointers, like where a function returns a negative value as an error instead of a pointer. So if you have a static analysis engine which runs scales to the size of the kernel, you can analyze each function. It's not super hard. In fact, I'm surprised that those bugs are not still exist in the kernel, because supposedly, I mean, it's relatively simple analysis, right? So you can figure out all these things. So for example, bugs like cancel delay work probably possible as well with slightly more sophisticated analysis, right? Of course, it's a good question, but kind of like enforcing buffer checks much harder, because we kind of like roots into the semantics of the program. Say, look, there's a buffer. You can, for example, start an analysis which tracks sizes of all the allocated objects and try to reason that this counter value can be reaching a value outside of the buffer or memory outside of the buffer. It's, however, a little bit complicated because it's more like a symbolic execution analysis. You really need to interpret all these statements and propagate the constraints of the counter variable, especially if you have loops or anything in the program. It gets a little it gets tough. It's also tough to scale to 27 million lines of code, right? So it's not always possible. But certain bugs, I believe, can be eliminated. Like race conditions are exceptionally hard because, you know, again, hard to understand semantics, right? Understanding something like this is also tricky because you really, I mean, what's the problem here? The problem stems from the fact that no one ever specifies even what the kernel is supposed to do. There is no specification. The kernel just does something. And it's a collective wisdom of people who develop the kernel to say, look, we believe that this is the right code and this is not the right version of something, right? But really, no one ever writes a specification saying that show transport handle will do yada yada, maybe it will print out like disguising handle and the whole value of the transfer in a buffer and will return it by performing security check. If you have the specification, then you can write an analysis and try to check whether the security check is in place. But no one ever wrote this specification. Right? That's, I mean, it's one of the problems, right? So we know like the problem is that we don't even know what each function in a kernel is supposed to do. And writing specifications is hard, so we'll get to that. So in this logical error, again, we've seen a couple of these in the past, you know, one spin lock instead of another. But again, it type checks. So whoever wrote this code just put out instead of like attribute a different variable attribute just for each of them used, right? It wasn't done. Okay. Checking this, really, the check is for attribute B, and we use that variable here. So it's probably nearly impossible to catch again with the goal of static analysis. Again, the reason I'm showing those bugs to give you a feeling of the complexity, you know, like if you want to be a bounty hunter and like find bugs in the Linux kernel, I'm pretty sure you will succeed. Like, and one of my students did it, right? I told you, Scotty was doing this. This kind of a bug where the program just forgets to check for the return value is probably catchable with static. So you just have to scale to the size of the kernel. But maybe you can say that any function which can return a null or a pointer should be checked for this point, right? So it's easy to program it. And maybe one team wrote it. So typically when the vulnerability is submitted or this bug fix is submitted, you will see the email and you can see that they like thousands of emails come from the same person. So most likely there will be a paper in the security conference that CCS or NDSS, which will talk about this analysis, right? Well, again, you can say maybe it's goofy, but no, apparently it happens. my lovely loop termination. You can say, okay, how can you forget the terminate loop? Well, it happens occasionally. Here's an example of infinite loop, because if you pass if you pass a zero value, apparently will not terminate. And it's still relatively easy, right? But this is another more involved loop termination condition. So again, it's not that I understand it fully, but the gist of it is that the kernel tries to restore floating point registers from the user space. If the kernel fails to restore the registers, it uses default in readable to check the number of faults that have occurred while reading the restore region, and only retries if no fault have occurred. However, if the range of memory that is checked is passed from user space and can be smaller than what is actually accessed, potentially resulting in a false negative. And the kernel then will be spinning in an infinite loop. So this is quite involved. So I kind of claim that catching this bug with anything beyond maybe formal verification is well, maybe possible, but it's super unlikely. Again, I know that some people in the class are doing fuzzing, so this is a useful kind of approach to think about fuzzing as well. So typically, I mean, in my view, when you want to build a fuzzer, it's better to know what is it you're looking for. So if you look at this classification of bugs, you at least can say, look, I want to hunt for example, missing return value checks, and your fuzzer should always fuzz around this memory allocation functions or something like that. Again, some maybe people who build fuzzers, they disagree, and they say, the fuzzing algorithm should be driven by whatever coverage or whatnot. So it's not about what we want to find. But kind of, I would guess that you still. Where's my HDMI? Yes, no. Really? We have to reshare. Let's see, share. Maybe it's share. Okay, cool. So and then as kind of a summary slide, this is the table which essentially summarizes the distribution of vulnerabilities in this analysis. Again, as I said, we only used device driver vulnerabilities or vulnerabilities in device drivers for the last 4 years. We found 240 of those out of maybe whatever, 3 times larger number. And among those, 120 were safety violations, 72 protocol violations, semantic violations, 48. And among those, the largest classes are buffer overflow here. Not surprisingly, you have to do the checks, but quite common also user for free. As I was saying, the second most, the biggest class is race conditions, 42, which is again not surprising because it's hard to reason about them, and especially legacy drivers, which were probably even implemented back where they were running on a single CPU and then patched later. Logical errors, since it's just a broad classification class, is quite common. Again, reference counting, surprisingly, is also hard to get right. So also lots of vulnerabilities. Okay, so now we kind of have a feeling of what can go wrong in the kernel, right? If ever in doubt, come back, look at this table, or look at this paper, it's published. Now the question is, okay, we all agree it sucks, vulnerabilities can happen, or those bugs can happen. The question is how serious it is. Does it really change anything in our lives? And the question is what do we know about attacks and defense? Well, last time I was trying to explain a little bit about possibility, what can be used and how those vulnerabilities can be used for attacking the kernel. But let's come back and revisit for a second. So, okay, so who can tell me what's the simplest attack? Your lovely workhorse. Or what is it you need to mount an attack? What's the prerequisite? Just to make it clear, so you guys, anyone who's doing security, is this stuff known to you? Exploitation, vulnerabilities, how to exploit stuff.
using some kind of code. Some kind of AC code that calls some kind of system call.
No, roughly speaking, correct. So you say, look, if I want to exploit something like this, you definitely have to drop the code which reaches this line, drop the input which reaches this line. But at a conceptual level, what you need, remember the table from the other paper which has signed, you need something like a write primitive. Essentially, the ability to write in memory. Sometimes it's more constrained. You can only write subsets of things. Or you need to do a read primitive, like these will result into something what is called information leaks. And we'll see that those are useful, for example, to break defenses like stack canaries, because you first will leak a canary and then use a write primitive to essentially smash the stack and do something else, right? But essentially your workhorse or a typical prerequisite for an attack is the write or read primitive. Sometimes if you want to exploit something like this, which most likely will only result in a denial of service due to a fraud or maybe some kind of infinite loop. You don't really do a read or write primitive. You simply reach this line without this flag, and then maybe it's erased in front of this. So sometimes read write primitive is not required, but if you want to like full control or information leak, you typically start with a read or write primitive. Again, like last time I was showing that the simplest write primitive is something like a buffer overflow. By the way, it's very common. We just said it's like the most common class. Okay, what do you do next? So what's your exploit from there? You found a bug. So you have your write primitive. So here, and here you can't eliminate. Is it a write primitive or a read primitive? Read, they agree. So it's because it dereferences the memory at the control counter with this one. Yeah. So what's the worst we can do is this attack? We can do an information leak, or what else can we do? Huh? Uh-huh. No, yeah, but then what's the tangible? Yeah, it's array out of bound. And okay, like maybe you can what kind of harm it can do to the kernel? Yeah, sec fault. So essentially will be a denial of service. The kernel will essentially, if you type the page which you know about, the kernel will say that by the way, it's page fault, I'm not exactly sure what's happening. And in most cases it will even continue running. But for example, if this code requires a spin lock on the path of this function, then the next piece of code which tries to reach this function again will be in a deadlock, right? Something like this. So okay, maybe this one is not very threatening, but let's imagine there is a buffer overflow which allows you to check to the right. Imagine there is an assignment there. So what do you do next? You have a write primitive. What's your goal? What are you going to be writing? Return address. Why? Correct. So essentially what you're saying is that imagine you want root privileges, as I was describing yesterday. Maybe you want to just reach this set UID function, which if you pass 0, maybe will make your current process the root. And so if you do a write primitive, again, being lazy, why not to just overwrite return address and jump to the set UID function, right? That's the easiest we can do. And you don't have to be like really sophisticated about it. There is an easy pass, go with an easy pass. Okay, cool. So we got it. So we can pardon. sorry, we can overwrite return address. What's the defense? Like if you were a kernel designer, how would you defend against the return address corruption?
Check some range.
Check the range, but how do you check the range? Like around every memory access? Oh, it's actually, it's doable. You can try to protect the stack. I would assume. I will explain how. Maybe you have an idea how. We can come back to it. So we can protect the stack by enforcing checks. What was the protection mechanism which I was describing last time? Do you remember? Yes, no? Remember, we talked about it, stack canary. Right, so stack canary is a technique which became deployed in all kernels and user level. So essentially, if this is the stack, remember, this is the return address on a stack. Stack goes this way. If it's really just a stack smashing attack, then you, for example, all the local variables will be allocated here. If you overwrite, then this will be a pointer to a buffer allocated locally on a stack. And if you do some kind of memcti, it will go this way. So if you, for example, add a magic value, which is canary, you basically know what this, like why do we use the word canary? You know the history of it. So really, like the miners were taking live birds and tiny cages down to the mines to detect the like essentially high level of pollution. The bird first collapses, and then the miner can escape. I'm not kidding. So that's why canary. And like pets were used historically for tasting the different poisonous dishes. They really took them to mines to check like accumulation. Helps you use this, I guess. Okay, so canary, right, works. It will not work with respect to like arbitrary write, but it will work to protect the stack. So essentially what happens here, how to implement it? Remember that when the compiler generates the code, you have control of what to do when you enter the function, which is called a prologue, and when you exit the function at the end, right? Typically, we see in x86, we maintain the stack frame, so we can save the old EBP pointer, set the new EBP pointer to the current value of the stack, and before we exit, we just return, right? So here, a similar instrumentation is used. However, this is like this is an example. Oh, it blinked. No, let's do it again. Oh. Yeah. Better. I'm curious if screen sharing. Okay, let's reshare again. So here we have this prologue and epilogue here, right, in a function. Let me just quickly grab annotation. So the compiler says, okay, I can insert some code here. I will reserve some space for the canary, for example, on the stack. And you can like instrument something called the exit from a function. And a specific instrumentation, which like, for example, GCC uses on x86 systems or GCC on x64 for user level code. And this is GCC on 64-bit machine for the kernel, is that it says, okay, I will keep around the canary variable. So it's relative to JS or fast registers, because these two registers are in at user level, they point to the thread local store. That's how we implement thread local variables, right? And so you can place the canary there. So here you first move the canary into the EDX register, and then you save it on the stack, right? Exactly. just moving it here from some other place to just TLS. And before exit, what you do is that you get this value from the stack into the EX register, subtract it, like essentially preventing the comparison from the same with the same TLS value. And if it's not null, then you go to the stack fail function, right? If you're an internal, you use a similar trick, but this GS register points to the first CPU set of variables, so essentially specific to the core. What we can observe here, I mean, it seemed to work, right? So you essentially, if someone smashes the stack like this, the canary will save you. This attack, however, is thrown to a couple of weaknesses, right? First of all, this variable, the canary variable, is initialized once the program is starting. So if you use a information leak attack, first leak the canary from your stack without smashing it, then you can construct the table in such a manner that it smashes it with correct canary, bypassing the protection mechanism degree. It just becomes a two-step attack. First, leak the canary, then second, smash correctly. And the second thing is that you can actually, for the kernel, I think it's lots of boots. I don't think they have more fine-grained canaries, right? So it's very possible. And there are also ways to brute force the canaries, essentially create, I think, fork forever. If you fork enough processes, you know, it's like, depending on how big the canary is, you can just brute force and guess it. And again, I'm not up to date on the current attacks and defenses, but just wanted to make sure that we understand that, okay, this is a possibility.
So the canary is safe to 2 so computationally it's hard to get the number.
Right, I agree, but here they don't use 256 as again, yeah, the size of the canary matters.
So we are not looking, we are not trying to get the 256 bits at a time. So because harder words at like 8 bits or something, so they are guessing us to match the first 8 bits. So it needs 256 tabs.
So you mean like you're trying to do a timing attack
Yeah.
to guess bit by bit? We should talk. I mean, I know that those are possible, especially like when you use timing to guess bit by bit. I'm not exactly sure that this is possible here, but if you've seen it, I trust you that might be possible. But I think it's like this is almost like a cycle level comparison. It should be, this is like one cycle no matter what, so I don't know. You can construct the timing attack, but maybe it's. And second, in our example, where if you, it really only helps against the very brutal right primitive where you're snapping the stack, where you're really overriding the local variable. However, if you have some kind of a array and you have a control of an index, then you can override more selectively. You really can keep just the return address.
No, okay, sure. A more advanced technique. So that was deployed for some time. Attackers learned how to bypass it. Then people came up with the next protection mechanism.
I mentioned it as well. It's called shadow stack. They say, okay, look, got it. So attackers can get the canaries. So why not to change the instrumentation slightly? And every time we enter the function, save return address in a separate memory location. It's somewhere completely different. And keep it there. That's our return address. And on the exit from function, compare the current value on our current stack here with this value saved on the shadow stack. And shadow stack only has return addresses, so it doesn't have local variables. Attacker doesn't easily like even if you smash this stack, these two values will be different, right? Agree with this? So this is called the technique of a shadow stack. It's reasonably lightweight, it's also deployed. What's the problem with this one? Well, you have to really hide the shadow stack from the attacker. You can either like randomly place it in memory, making sure that the attacker cannot guess where it is, and then use this array primitive to override the shadow stack. Otherwise, if they know the value, they just like override it or override false or something. Set override there is. I mean, it definitely complicates life. and or use some kind of compiler instrumentation similar to what you suggested here to make sure that no instruction and or maybe some hardware support to make sure that no new instruction can reach the shadow stack. Okay, cool. Shadow stacks they are used right successfully. So again, quite a bit of advanced technique. So, and if you get to shadow stack, then you can very well say, why not to enforce the control flow, right? Because in my kind of story, I always say, well, attacker will go off through the return address. But that's just one flavor of creating control flow. What are the other flavors? How else attacker can get to set UAV, for example? Remember your goal. Goal is to get to set UAV. I talked about overriding return address in the stack. Well, seems it's a little complicated with the shadow stack. How else you would do it? I mentioned it last time as well. Just wanted to make sure that we come back to it. No memory. Well, you can try to go for any pointer in the program, any function pointer, any, like if you have a struct, remember I said, struct file, which has two function pointers, like read, that's a function pointer, and write. And you have an instance of this file data structure in a heap. Why not to overwrite one of those pointers? And then trigger a pass which invokes the read. And if this read points to set UID, your goal probably is achieved. It's not always trivial like that, but you can take, you don't have to go just for the return addresses. You can also override other pointers. Agree? And especially like in languages like C++, there are these virtual tables, stuff like that. So pointers are abundant. You can even find a function which matches the function signature, which means that it will correctly execute. So that's cute, right? So, and then of course, so people started doing it. So don't only go for this return addresses, just go for any pointer, or sometimes I'm not an expert, but sometimes the code is generated like jump tables and stuff, and you can remember PLT tables, like for the position independent code, not PLT, but what are those PLTs for resolving the variables, but you will find some pointers which you know, so you can think about. So people came up with the next level of techniques. It's called control flow integrity, right? So at compile time, for example, if there is an invocation of this read pointer, you have a file read invocation in your code, right? You see it, line? You will do instrumentation here to check that this read pointer which you're trying to invoke matches the expectation, meaning that your static analysis will generate some kind of, or a compiler class will generate some kind of table which says, okay, in practice, this invocation of a first entry in a table, right? And tables may be like read-only, so attacker cannot really override these pointers, right? Or you can do a comparison as well, saying that pointer hasn't changed, right? So this will enforce the forward edge of the control flow. For the return edge, you will use the shadow stack. Essentially, this way you cannot override function pointers in the program, and at the same time, on the return pass, you cannot smash the stack. Agree with this? Cute? It turns out that this technique does not incur that much overhead because, I mean, there is overhead, but and I cannot say immediately off the top of my head, but in the Linux kernel, in the kernel itself, I don't like shadow stack is almost no work. It's pretty lightweight. Just a couple of instructions to compare. It depends on how well you want to protect the shadow stack. So if you really want to hide it, then you have to, like, in front of every move instruction, you must check that it doesn't go to the shadow stack. That's a little tricky. So yeah, that may incur overhead. And I'm also like, again, I'm not up to date with those mechanisms. Like I have a historical perspective, but
if you have this question, it's a good research project. Just like dig the literature and see what the overhead is, what the protection mechanisms in the kernel today, and what is considered to be in the kernel tomorrow. And Android will use a different set of protection mechanisms compared to, like, say, Linux kernel compared to iOS, because all of them are slightly like different companies, different tool chains, different trade-offs. But probably not a ton of overhead, so it's still deployable. I don't think, like, to be more specific, I think Android at least promised to deploy a technique which is called code pointer integrity, CPI. Protect every pointer, code pointer in the code. It's a famous paper from a team at EPFL by George Kandea and his students. And I don't want to cover it, but we can go into it. So essentially, there's a way to protect every pointer in a program, like to make sure that they are all, like, exploitation becomes kind of complicated. But even like where I want to get is to something different. So imagine you have a program. Imagine all control flow transitions are somehow guarded. There are some kind of like arguments here saying that, first of all, your analysis will often over approximate, and there were papers even for the kernel where they say, look, it's called control flow bending. So essentially, despite the fact that you have this table, there is enough imprecision in the control flow transitions that you still can exploit them. And it's a good paper, again, from Kim from Georgia Tech. So worth reading, like, to understand how control flow can do that. But imagine even if you have completely full control flow enforcement. Actually, I wanted to first go to a slightly different set of attacks, which are also like kind of cool. Before we even get to this, so, and I skip like a whole class of attacks. Okay, remember this figure for a sec. Let's go back for a second to stack smashing attack, and imagine we don't have any of those enforcement mechanisms, but it's just that this technique is so important that it's worse than this. So we said our goal is to get to set UID of 0, right? Originally, when we were doing stack smash. Imagine the stack is still wide open, unprotected, no canaries, or you know how to bypass. There is a return value here. Imagine for whatever reason, you either don't have a function which you want to invoke immediately. No, maybe the kernel just simply does never invoke set UID, or maybe every time it invokes the set UID, the value is non-zero. So at least to make sure that if you want to pass 0, you want to push 0 on a stack first, or something like an argument, right? And then invoke set UID with a colon stars. So you want to do like a tiny computation, right? Before, like, maybe you really want to do like a Turing complete thing. Maybe you want to do something. Okay, so a typical trick in the past was that this return errors which you're smashing will actually lead you kind of back to user. I mean, there is multiple things here. So for example, first of all, if you smash the stack with like some buffer, you can say, look, I can smash it with garbage, but you can also provide something what is called the shell code. That's exactly the code which you want to execute. So that's your push. So why not to provide it yourself, right? Why complicate stuff? You say, I will smash it with push 0 and then call set UID, right? Agree? And it makes sense. And then I return immediately here, right? If you can guess the average of the stack, you can return and start running whatever you provided, right? Agree? Huh? Yeah. It used to be easy. That's why I wanted to talk about it.
just to make sure that we understand. Okay, if stack is mapped as executable memory, it's easy. If it's if it's only mapped as writable memory and readable memory, but not executable, then it fails because you say, look, I cannot do this, right? But then you say, look, what if I return back to user level? Because at user level, you have executable memory, and maybe you like kind of like have this. If you blindly say that, okay, why not to return directly to user? Because like it's the same page table, you still remain. It's not like you're returning from an interrupt here. You just do a return. You're just jumping effectively to this state and privilege 0, and still running the code which you with our can provide, right? Right? They agree with this? So easy, and then you can do anything, right? That's your computation here. Of course, you say, look, they came up with this idea that there was a couple of things, a couple of evolution of this needs, which I skipped and I wanted to come back. Let me just show them to you. So first of all, they came up with this idea, support or WXOR X. So it's practical XOR executable. So essentially meaning that the pages or it's alternatively called data execution. Essentially the code is either mapped as writable or as executable. So which means that the user cannot trivially construct this payload, because if the user can write into those pages, it's writable, which means that it cannot be executed, right? Makes sense. And so it looks a little bit archaic after all, like kind of old integrity, but back in the day, it was actually deployed. It's still deployed today. So to make sure that we have this line up, and when you see this DEP thing, you understand what's going on. So it's essentially to complicate the hacker's life, to make sure that if the hacker wants to execute some sequence of instructions, who falls that UAD, it's not as easy. So you cannot at least like jump back to user level and it's executed, right? And you cannot jump to the stack because stack is also writable, so not executable, right? They agree? So that's kind of cute. Okay. However, there's this ingenious way of how to actually still construct those computations without actually the need of without the need for modifying any memory or any code. So does anyone know how to do it?
Yeah, just put like some no instruction something like this. And enter this will put it.
Say again.
Putting like no instructions there, like not.
So this is the stack. We cannot put anything on the stack what we can execute. We cannot at user level. You can probably jump to user code, and if it's not writable code, but really code is something like libc or something, then it's executable from a kernel. So you can return here. But still, how to like if you really want to do something like push 0 and then call set UAD, can you do it? You have yeah. Correct. So what I wanted to explain is this technique which is called return-oriented programming. So who is familiar with this? So Jerry knows something. You also know something. Zapunk knows everything. The idea is the following. So that's the paper which, I mean, the technique was known before, but this is the first paper which clearly explained this and explained that this general thing. Essentially, we present new techniques. We present new techniques that allow return into libc attack. This is my return into libc. So that's kind of like to be mounted on x86 executables that calls no functions at all. Okay, let me explain how it works. The idea is that you can construct Turing complete computation out of the code which you already have in your program. So this is an example from a paper. So for example, somewhere in the beginning, in a prologue of a function, this is the assembly sequence, which if you disassemble reads like test 7 with EDI.
and what set non-zero byte. I don't even know what this set NZB instruction is, but some instruction, right? However, the property of x86 machine is that if you start interpreting these instructions from not from this F7 byte, but from the C7, from this one, this set of instructions suddenly turns into something completely different. So the last C3 suddenly becomes a ret instruction. This 45 is increment of EBP. 95 is exchange of EBP and EIX. And this one is actually move of a zero, oh no, F0 into EDI. Completely different instruction stream, right? And what these authors are doing, they say, look, if we start staring very carefully at the instructions which always end with a return, we can figure out some small computation before the return, right? The question is like, how can you construct a Turing complete computation out of it? Do you have an idea? Sure. Right. So if you can find a gadget which moves something somewhere and then return, and another maybe gadget which does some addition and then returns. So then what? Anyone remembers? Jahan, you tell us.
Because you have full control of the stack and the spring goes after you install.
Correct. Since you're looking for the instructions which end with a ret will like essentially pick a value from the stack and jump potentially to the next gadget. And this gadget will maybe place something in registers, maybe we'll place something on a stack, but then again, it executes a ret and we'll jump to the third guard, right? So you kind of, instead of like typing the program instruction by instruction, you use this kind of a stack machine, where you say, by controlling this stack, I will stitch those together to make sure that I have computation which I want. And in a typical program, the observation was, that was their claim, that in any sufficiently large body of x86 executable code, there will exist sufficiently many useful code sequences that an attacker who controls the stack will be able, by means of the return to libc or return related programming techniques which they introduced to cause the exploited program to undertake arbitrary, they don't say Turing complete, but Turing complete computations. Here's an example. So this is a gadget which loads the constant into the EDX register. They just, and say, wow, they don't do this manually. Immediately came out with a compiler, which disassembles an executable, searches for gadgets, and then there will be a compiler where you type a normal program in a normal language, imperative language, and then it will compile into those gadgets in this stack machine. So for example, this, didn't even touch it. Okay, it was probably fast enough that it didn't disconnect. So here, this notation means that a value on the stack points to the beginning of this gadget which they try to use, and this is the ESP value. So if this executes like the previous gadget, right, which lends us, well, we'll pop this value, right, jump to the beginning of the gadget. So our ESP will be pointing right here. Pop will load this value into the EDX register, right? Agree? So you just moved a constant into a register. That's the gadget. Well, slightly more complicated gadget, but again, I will only go through simple ones. So in this example, this is the first gadget, which so it says load a word of memory into EAX. So what happens here? We start executing this gadget, we will pop the value which is stored here into EAX, right? Agree? This value should be carefully chosen to make sure that it will be plus 64. And the reason plus 64 because our other gadget, so it has to be probably minus 64 or something, right? We'll execute this. So it will essentially move from the pointer location pointed by the EAX plus 64 into EAX. So essentially, if you carefully compute this value, which points to this deadbeef, right, minus 64, then you will get deadbeef into the EAX register, right? And so on and so on. So I didn't go into the paper, something lecture in security possible to make sense. They show you how to construct even now statements, which is kind of finding through the screen, but you can. And if you like, it's kind of very, very cute. So suddenly you say, look, I don't really need to provide any shell code. By controlling the stack and knowing the gadgets, I can construct any arbitrary computation. So if I need to execute push 0 and then call set2ad, I can easily do it through this technique. So it's called return-oriented programming, right? Got it? Everyone is on board? Of course, return-oriented programming is defeated with my first even with the canaries, second with shadow stacks, and by extension, okay, like I don't know if they're gonna use forward edges, probably they do in some flavors. Just wanted to make sure that we understand this technique. But again, very powerful exploitation technique, meaning that you can run something and the computation can be hiding on a stack. So you didn't change the code of the program which you load in memory. It's just that by controlling the stack, the stuff which you want to execute executes. Okay, but I wanted to come back to this control flow integrity. Again, imagine now you're so powerful that every pointer, the control flow, not every pointer, but control flow of the program is completely locked. So somehow you figure out a way through this code pointer integrity, protection of the forward edge, and protection of the return edge, that your program is like completely locked into whatever transitions between those, like that's the control flow graph. Now what? How can you exploit now? Now Jafank will tell us. Yeah. Okay, then let's let everyone else to think about it for a second. Again, your goal, for the sake of it, is to do this set2ad of 0. But you can't jump to it. You can't put it on a stack, right? Because control flow is enforced. So how can we do this then? Look, those attacks also were known in their simple form. But then they kind of, now they exist on steroids. Any ideas? Anyone heard of data-oriented programming or data-only attacks? So that's the trick. So you say, look, I cannot overwrite pointers in a program. Those are protected. You can only overwrite data. The question is, can you find a path through existing control flow, which still somehow, maybe through like concept like intermediate stages, will somehow lead you to this set2ad with this valid argument? The answer will be maybe. It's not always possible, but in many cases, the computation which can be constructed on top of existing control flow by only manipulating the data of that program is powerful enough to do almost everything what you want. So this is called, the flavor of those attacks is called data-only attacks, because you don't change the pointers like in a classical exploitation way. You just change the data. So it's again, it's not the very first paper on this subject. It's one of the first which essentially those techniques. They existed. People were just essentially using very short sequences where you say, look, if I override this variable, let's say it's A, and you suddenly have some kind of a code, if A equals to something, let's set you a B of A or 0 or B, then maybe you need to override B and A simultaneously. And then, you know, typically for a human, you can only like reason for a short difference from the right primitive to this gadget which you want to exploit. So we will call those sequences which are called gadgets, but the idea here is that the authors of this paper, they come up with this hypothetical source code, they say a web server or something. So this FTP server. This server executes some kind of a loop by counting connection limits, like for as long as this thing is not 0, it keep counting whatever, keep executing the loop, reads data from a socket into a buffer. Something is like some code is essentially if you do reference into a buffer, and if type of the request is none, you break. If the type of the request is stream, then you what is SRV? Not sure. Pointer to a server, I guess. Current max. Like you do something. If not, if it's not a stream, then you assign a type to a server, increment some number of total bytes and stuff like that, right? So kind of like a code which you possibly wrote for a homework assignment or maybe for a production system. It has a buffer overflow because essentially attacker can control, like essentially if you like essentially sending a specific request, it will read into a buffer without like checking the length, which means that those variables are under attacker controls and attacker can override them. Now what? The ingenious observation which this paper makes is the following, that this code is essentially implements a slightly completely looking different code, which updates a list. So it's essentially a function which takes a head of the list, a constant, and essentially loops through the list, taking the next pointer in the list, and increments every list field as the constant. You see the equivalence. So essentially, you say, look, I have an infinite loop. This is where's my next here? Let's take a look. Let's convince ourselves that it's the same code. So this, obviously, this addition, let me just quickly erase everything on this screen. So this addition is this operation, right? Where do we get the next? Is this your next? Yes or not? So we have a condition. So essentially, if type is okay, if we don't see it, let's just quickly stop the slideshow. Go back to the paper because I just copied it from the paper, so we'll be able to see it in a second. Using security, let's assume this one. I was going through this various flavors of those data-oriented attacks. Maybe this is the page. Well, that's the newer paper. This is this one. So maybe this one. Yeah. So this is the equivalence table for this specific code. Let me just share it for the Zoom people. So here we say that if list is null, let me maybe highlight it. If list is null, this if type is none, then break, right? So that's the equivalence. Assignment is this, service equals to list. This is the addition. Next operation is this, size, current max, the reference of this pointer. Agree with this?
Oh, maybe it's a little bit hard to see, but started. So essentially, by controlling the values of this variables, local variables from the stack, you can construct a completely different computation, right? Well, it was hard, maybe unless you really like the skillful attacker, it's so complicated. So people came up with the technique which automates it. So first of all, is it clear? This is essentially, if you want to like walk through the list in memory of this program, and you only overwrite data, it's only force control loop. This loop is a completely legal this program. So now those previous techniques will help you to stop this computation if attacker overwrites the with the buffer overflow, the stack buffer to overwrite this local variables. Agree? Yes.
And so what people started doing is that they said, okay, we're gonna be using those and stitching them together, sorry, to make sure. Just do this. So, if it's hard for a human to figure out how to construct those apps.
So another team, so Matthias was here a couple of weeks ago, visited the past, gave a lecture on fuzzy spin. Grant Jagger is my buddy from Penn State University. If you carefully look at my papers, you will see a lot. Essentially, the idea is that they say, look, since control flow integrity is commonly enforced in programs, it's hard to attack. So they say, okay, look, we will come up with this compiler, which they call POP-C, which will allow you to essentially analyze your program for existence of those gadgets. They use symbolic execution for analysis, kind of like you say, you type a program in a regular language, saying, hey, maybe I want to push something on the stack, then you execute set to ID, and you have a write primitive in the program, right? Then they say, look, we will allow you to construct the computation. Sometimes it involves like multiple iterations of this computation, and they come up with abstraction of registers. And those registers, more like CPU registers, they're just values in like different fields spread across this program, in which they say intermediate state. But then eventually, in most cases, I don't think they have a proof that they are Turing complete or that they will ever succeed. But in most cases, the symbolic execution engine allows you to compile your computation on existing, using existing gadgets, and then essentially execute this computation. And that's pretty amazing because you were saying, okay, is that what will be a performance overhead of enforcing like shadow stack or enforcing code pointer integrity? So supposedly, shadow stack is just 1% of performance or less. Code pointer integrity, which I did not explain, but it protects all the pointers in the program, is still reasonably efficient. But if you want to protect data, so essentially, if you really want to enforce the fact that like all the writes or all the pointers are protected, then it takes like forever. And like that's essentially no one does it in practice. And so those data-oriented attacks today, I think, I mean, I didn't read the most recent literature, but from my understanding, there is no elegant way to essentially defend against them. And so those are like, plus we have this high degree of automation, which allows the person to take a compiler, take a look at the program, and we'll just compile it with the computation. Just simply say, okay, override this variable in memory, and you will be told that it will be like whatever function in the case. Okay. Okay, so this is what this is all what I wanted to cover today. So essentially, that was my quick kind of introduction to possible exploitation techniques. Just wanted to leave you with this block-oriented programming thing. I think this code pointer integrity, which I didn't cover, is deployed on Android systems, which significantly complicates. I think all of these techniques, like shadow stacks, code pointer integrity, and everything, is deployed. Besides that, there is no technique for protecting against data overchecks. So with that, okay, so what can be done? You have a kernel. We saw a bunch of bugs in the kernel. Like I show you, like maybe 10 or something around classes, 240 vulnerabilities just in device drivers. Some of them quite involved. Maybe not all of it is exploitable, but likely many of those are. So as a system designer, what is it you're going to do? How to protect your kernel from those exploits? By the way, do you understand that, like, if I find an exploit in a kernel, I own the machine. Sometimes I own the machine remotely if I find the exploit in a network stack or something what is reachable from a network. So what's your next step? What is it you're doing? Since you already did brains, so who is doing fuzzing? One person? You're a minority. Yeah. Fuzzing and automated testing will help you to find more attacks. If you listen to Matthias, even he admits that, well, maybe we're at the end of the ride. So we're approaching the limits of fuzzing. I'm not an expert. So you maybe myself, Matthias, and everyone else are simply wrong. And those testing techniques will iron out enough bugs that the kernel suddenly will become, bulletproof. I think highly unlikely, because the bugs will be lurking somewhere deep in the code, so hard to reach, stuff like that. But still, it's a valid technique, right? Fuzzing or testing. What's next? Sorry, no, yeah. Oh, yeah. That's and it was actually better. They were trying to run it. Yeah, not surprising. So like LLMs can probably uncover some fraction of bugs. It's hard probably to still analyze what is a false positive, right? I think it's like that. Yeah, but yeah, I didn't read, but it's believable. But okay, so sure, testing. What's up? What else? Because that will map the end of the rest of the semester. Roughly will be guided by what is it we need to do. George has an idea. Verification, correct. Verification suddenly became practical. So you can really reason about correctness of a program if hopefully I will get to it, which is most likely some basics of verification, and then like it's doable. You can have mathematical proof. First of all, write a spec about what the code is supposed to do, and second, you have a mathematical proof that it actually does what it's supposed to do, right? However, verification is still like today still doesn't scale to the kernel, right? So you might verify some bits of the kernel. If we're doing verification of device drivers, some people verified memory allocator, stuff like that, right? So it's doable, but not all. And what else? What was historical technique for improving security?
Well, the technique is isolation. So the intuition here is that if you write parts of exploitable or potentially exploitable code in isolation, it at least will be like maybe there is a write which allows to overwrite memory of this subsystem, but it's harder to escape the isolation bound, right? And so, for example, we run individual processes for each web page in the web browser. You know, people isolate parts of the rendering engine, use WASM to deploy computation, trusted computations, like first to isolate parts of the web browser probably as well, but maybe not use for production, but run some untrusted pieces of the code at the edge of the network, stuff like that, right? So our next topic, kind of like the reason I was explaining bugs is that we're gonna look at these two. So we will look first at isolation and try to follow the line of kernel work, which was trying to implement kernels, and the specific architecture is called microkernels. So kernels which run like individual subsystems of a kernel in isolation, and how this can be done. Essentially, that's the topic for next Monday. So I'll stop here, and then see you then on Monday for microkernels.